Think about what you picture when someone says medieval monastery. Stone walls rising 3 stories, candles pushing back the dark, monks moving through corridors in wool robes, winter piling against the windows, and somehow, through all of it, warmth. That image is mostly right, but history taught you the wrong reason for it. The warmth was not the fire. The fire in most monasteries was nearly out by midnight. The wood was expensive, the supply was limited, and the monks who managed those buildings knew you could not burn your way through an English winter forever. What kept those monks alive was not the flame. It was what the walls and floors had swallowed during the day. Medieval engineers solved the heating problem permanently. No monthly bill, no service contract, no supplier who stopped delivering when the roads iced over. And the exact reason you are still paying hundreds of dollars a month to stay warm right now, while their solution sits unused in every hardware store in the country, comes down to one decision made in 1894 that is coming up in about 60 seconds. Because the average American household spends close to $1,000 a year on space heating alone, according to the U.S. Energy Information Administration's 2023 Residential Energy Consumption Survey. The Cistercian monks at Fountains Abbey in North Yorkshire, who maintained their calefactorium, their single communal warming room, through English winters from the 12th century forward, paid nothing. Not a lower rate, not a seasonal discount, nothing. Not the army that protected them, not the plague that surrounded them, not the enemy at the gate. The thing that nearly broke those communities was the cold, and the ones that survived solved it for a cost you could carry in one hand. There is one specific decision those monks made about what went into the floor of that warming room that made permanent free heat possible. Not a theory, not a reconstruction. A documented physical structure that English heritage archaeologist Glenn Kopak excavated in detail and published in his 1993 study, Fountains Abbey, still available through English Heritage's own publications today. That structure is still there. You can walk through it. There is one more thing worth knowing before the build. Most people who try to replicate what those monks built get one step wrong. It is the first step. It is the difference between a system that heats your home through 4 decades of winters and one that fails before February is over. That step is coming up exactly when you need it. What buried this approach permanently was not a scientific discovery that made it obsolete. It was economics. Pure, simple, documented economics. The American Society of Heating and Ventilating Engineers was founded in 1894. Within 2 decades, the industry they represented had successfully repositioned passive thermal storage. The exact approach the monks at Fountains Abbey built into their floors was primitive, insufficient, and beneath the standards of a modern building. The U.S. HVAC industry today generates approximately $168 billion in annual revenue, according to IBIS World's 2023 HVAC industry report. That number depends entirely on a house that cannot hold its own heat, a house that gets cold the moment the system stops running, a house that needs a filter replaced, a refrigerant line charged, a heat exchanger swapped out every decade. Intact, medieval calefactoria cannot be invoiced. Not struggled with, not upgraded, cannot be invoiced. The warming room at Fountains Abbey has never had a maintenance contract. It has never needed one. The physics built into its construction in the 12th century is still operating. Every time a Yorkshire winter presses against those walls, the stored mass in that floor pushes back with the same principle it was built on 1,000 years ago. You cannot sell a subscription to a stone floor. You can sell one to a forced air furnace every single season. The passive thermal approach was not wrong, inconvenient. Those are 2 completely different things. And the billing cycle simply did not have room for free. But here's the part the industry hoped you would never ask. Exactly how it worked. That is what comes next. This is not a new idea. The Romans built hypocaust systems, raised floors with hot air channels beneath, documented in extraordinary detail at Roman Bath in Somerset, and recorded continuously by English Heritage since 1983. The Islamic world carried that knowledge forward into the medieval period. Al-Jazari's Book of Knowledge of Ingenious Mechanical Devices, completed in 1206 and preserved in the Chester Beatty Library in Dublin, describes thermal mass floors in public bath design as standard engineering. Not innovation, standard practice. And the Cistercians took it further than anyone. The Rule of St. Benedict, written in 516 CE, and the founding document of every Cistercian community in medieval Europe, mandates exactly one heated room per monastery, the calefactorium. One room. Not a network of furnaces burning through the night. One room, engineered to hold heat so effectively that a morning fire could carry warmth through to the following day. Glenn Kopak's archaeological work at Fountains Abbey, published by English Heritage in 1993, documents the calefactorium floor construction specifically. A compacted layer of dry sand underlaying the stone flags, creating a thermal reservoir that absorbed heat from the fire above, and returned it slowly from below through the night without a single additional piece of fuel. That is the entire principle. Those communities did not survive the winters because they burned more wood. They survived because they stored what they had already burned. During the Great Famine of 1315 to 1322, documented by historian William Chester Jordan in his 1996 study, the Great Famine in Northern Europe in the early 14th century. Communities without that thermal storage lost people to cold on top of starvation. Communities with it did not struggled through, died. What medieval engineers understood, and what you're about to build for under $200, starts with one physical fact so simple it fits in a single sentence. Sand stores heat the way a cast iron pan holds temperature long after you turn off the burner. That property has a technical name, specific heat capacity. But the name does not matter. What matters is the physical reality. A drum of dry construction sand weighing 200 pounds, heated to the temperature of a moderate oven, holds roughly 8.5 kilowatt hours of thermal energy. That is enough heat to warm a small room for a full day. Released slowly, released passively, released without the heater running at all. According to the EIA's 2023 Residential Energy Consumption Survey, the average American household spends $950 a year on space heating. Medieval monks at Fountains Abbey spent nothing. Without a bill, without a supplier, without a service contract, and almost nobody's using it. You've seen this principle your whole life, just never connected the dots. A thermos does not generate heat. It stores what is already there and releases it slowly. Your oven preheats for 20 minutes and takes 40 to cool. The dense walls inside are doing exactly what the sand layer under Fountains Abbey's flagstones did. A brick pizza oven holds its temperature for 3 to 4 hours after the fire dies. Ask any wood-fired pizzeria owner, and they will tell you the brick is doing more work than the flame ever did. The sand battery is a thermos, built for your house, charged overnight, releasing heat slowly through the following day. Most people who try this get one step wrong. It is the first step. It is the choice of sand, specifically whether it is dry. Here's what you need. I want to be honest about every number. One clean steel 55-gallon drum with a removable lid, available at farm supply stores and hardware chains for between $40 and $60. One 1,500-watt stainless steel immersion heater element, the type used in domestic hot water tanks, available at plumbing supply stores or online for around $30. One roll of 4-inch rock wool pipe insulation, 2 6-foot lengths, around $30 at any building supply yard. One plug-in digital thermostat controller, the type sold for electric smokers or fermentation temperature management, around $25. 200 pounds of dry construction sand, sold by the bag at building supply yards, not play sand, under $20. One small 12-volt computer case fan and a 2-foot length of flexible copper pipe, under $30 combined. Total, under $200. Here's the one thing most people get wrong. They use damp sand. This matters more than any other variable, more than the drum, more than the heater wattage, more than the insulation thickness. Wet sand fights heat instead of storing it. Water trapped in a thermal mass turns to steam when the temperature exceeds boiling point, which wastes energy and creates pressure the drum was not designed to hold. Glenn Kopak's documentation of the Fountains Abbey calefactorium floor specifically notes that the sand layer was compacted and left to fully dry before the flagstone layer was laid above it. The dryness was not incidental. It was the engineering decision that made the whole system work. Test your sand before it goes in. Grab a handful and squeeze it firmly. Open your hand. If the compressed shape holds even slightly, the sand has too much moisture. Spread it on a tarp in direct sun for a full day. Test again. When a squeezed handful collapses immediately into loose grains as you open your fingers, the sand is ready. Build it the way most people do, with sand pulled straight from a bag left outside. And you get what the failed monastery heating attempts got. Build it the Fountains Abbey way, dry, compacted, sealed, and you get what the calefactorium still has today. Now, seal the drum base. Use metal foil tape, the heavy HVAC rated kind, not standard duct tape, and run a complete seal around the inside bottom edge of the drum. Press it firmly into the seam. You are creating a permanent moisture barrier. This is a one-time task. Do it completely. Install the heater element. Measure 6 inches up from the bottom of the drum and drill a hole sized to match your heater element's thread diameter. Thread the element in from outside using plumber's thread tape on the fitting for a watertight seal. The element sits horizontally inside the lower third of the sand column. This positioning is used in commercial sand battery installations, including the Polar Night Energy Facility in Kankaanpää, Finland, commissioned in 2022, the first utility-scale sand battery in operation, and the thermal geometry it creates mirrors what Kopak documented at Fountains Abbey. Heat rising through packed granular material from a low source point. Fill with dry sand. Pour the prepared dry construction sand in layers of about 4 inches at a time. After each layer, press down firmly with a flat board. You want consistent granular contact throughout, not airy pockets, not brick-hard compaction. Stop filling 4 inches below the drum's upper rim. That air gap protects the lid seal from direct radiant heat. The next step is the one most people skip. It is also the one that made the difference between a monastery that held its community warmth through a Yorkshire February and one that did not. Install the heat exchanger before sealing the lid. Coil a 2-foot length of flexible copper pipe into a loose spiral roughly the diameter of a dinner plate. Lower the coil into the upper third of the sand column, buried but accessible. Leave both ends of the pipe protruding upward through 2 small holes drilled in the drum lid. This copper coil is your heat transfer loop. Air moving through it picks up thermal energy from the sand and carries it into your living space continuously, without requiring the heater element to run at all. Mount the small 12-volt fan at the inlet pipe end, directing airflow into and through the coil. The outlet pipe can pass through a drilled hole in an interior wall, or simply radiate heat directly into the room where the drum sits. For a workshop, garage, or single room, open radiation from the outlet pipe is sufficient without any wall penetration. Seal the lid around both pipe penetrations with metal foil tape. Wrap the outside of the drum entirely in rock wool insulation. Secure it with metal strapping or additional layers of foil tape. The insulation is not decorative. It is the reason the system continues releasing heat in January rather than losing it to the surrounding air within an hour. The monks at Fountains Abbey achieved the same effect through sheer mass. Walls 4 feet thick act as their own insulation layer. You are compressing that same principle into a drum you can move. Run the temperature probe from your thermostat controller through a small drilled hole into the sand at mid-drum depth. Set the controller's upper limit to 200 degrees Celsius, roughly the temperature of a moderate baking oven. Connect the heater element in the thermostat to a simple plug-in timer set to run during off-peak electricity hours. In most U.S. regions, off-peak rates run from approximately 11 p.m. to 7 a.m. at around 8 cents per kilowatt hour. The drum charges over 6 to 8 hours. The thermostat cuts power the moment the sand reaches its target temperature. When you run the fan at 7 in the morning, room temperature air pulls through the copper coil. It exits warm. It keeps exiting warm for 12 to 18 hours without the heater element drawing any power at all. 1 unit does this for 1 room. What a family of 4 does with 3 of them, positioned in a central living area and 2 sleeping spaces, changes the entire heating calculation. And what the Cistercian monks at Fountains Abbey did with the same thermal mass principle across an entire settled community, and what that same logic means for your street today, is the part that changes how you think about the whole problem. 3 drums, charged overnight at off-peak rates, store enough thermal energy to run a standard 3-bedroom house through a full winter day. The charging cost for 3 drums at 8 cents per kilowatt hour runs to approximately $1.60 per night. For a 30-day winter month, that is under $50 total for the whole house. The EIA's 2023 survey puts average American household heating costs at $950 a year. $50 a month through a 5-month heating season is $250. No bills at the scale those monks ran, no dependence on central infrastructure, no service contract that expires in November when you need it most. Scale further. 20 households on a single street sharing 1 large communal sand battery, the size of a small garden shed, built over a weekend from the same materials in larger quantities, and you have the Cistercian monastic model running exactly as it was designed. The community that heats together cuts costs to nearly nothing per household. That is not a modern co-op concept. That is the documented operating model of Fountains Abbey in the 12th century. There's one condition where this works less well. Medieval engineers knew it, and the way they solved it is the last thing in the script. In regions with persistently high ambient humidity, coastal climates, areas with saturated ground air through winter, moisture infiltration into the sand over time gradually reduces the system's thermal performance. The sand absorbs atmospheric moisture slowly, year by year, and wet sand stores less heat than dry. Glenn Kopach's documentation at Fountains Abbey notes that the sand layer beneath the calefactorium floor was relayed and re-dried approximately every generation, roughly every 25 to 30 years, as part of the monastery's normal building maintenance cycle, not emergency repair, scheduled maintenance. For a home drum system in a humid climate, the fix is simpler than anything the monks had to do. Every 3 to 4 years, on a dry summer day, open the drum, spread the sand on a tarp in full sun for 8 hours. Let it dry completely, repack, reseal. The whole process takes an afternoon. That is the full maintenance requirement for a system that otherwise runs continuously for decades without attention. The calefactorium at Fountains Abbey still stands. The sand is still under those stones. The physics that made it work in the 12th century has not changed by a single variable. What you built does exactly the same thing. Medieval engineers did not solve this because they were more patient than you or more clever than you. They solved it because they did not have the option of a November invoice. The problem required a permanent answer, and they built one. That answer worked for communities living through the Great Famine, through the Black Death of 1347 to 1351, through every English winter the 14th century could produce. It was never wrong. It was made inconvenient. The physics was always there. It was just waiting for someone to use it again. I don't know what brought you here. It doesn't matter. It works either way.